Welcome to Your Math Explained, where we make math simple and clear. My name's Angela. In the last video, we got an introductory look at what the double angle identities are and how we can use them. We also proved the double angle identity for sine 2x and one of the cos 2x. Today, we're going to prove the rest of them, and we're going to take a look at how we can incorporate them in harder problems. So our first problem here is to prove the double angle identity for tan 2x. So what we're going to do is we're going to rewrite this as tangent of x plus x. And then we're going to go use our sum of difference identity to rewrite this. So this is equal to tangent of the first angle, which is x, plus tangent of the second angle, which is also x. And this is over 1 minus tangent of the first angle multiplied by tangent of the second angle. So then our numerator, we have 10x plus 10x, which is just 2 10x. And then our denominator is going to be 1 minus, and 10x times 10x is going to be tangent squared x. So this is the proof for our double angle identity for tan 2x. The next one is our cos 2x. So in the last video, we already proved the first part. We proved this one. So that is going to be our starting point. So we have cos 2x is equal to cos squared x minus sine squared x. And then in the last video, I hinted at that we can get the other two simply by using the Pythagorean identity, which is sine squared x plus cos squared x is equal to 1. So what we're going to do is we're going to isolate sine squared x. So then we get sine squared x is equal to 1 minus cos squared x. So this is one of our equations. Now we can do the same thing and we can isolate cos squared x. So if we do that, we get cos squared x is equal to 1 minus sine squared x. So this is going to be our second equation. Now if we take our first equation and do our substitution, so if we substitute the expression 1 minus cos squared x into sine squared x, what we're going to get is this is equal to cos squared x minus, and then in bracket, we're going to have 1 minus cos squared x. So now simplifying this, we get this is equal to 2 cos squared x minus 1. And then we can do the exact same thing. So we start with cos 2x is equal to cos squared x minus sine squared x. But this time we're going to substitute the expression 1 minus sine squared x into cos squared x using our second equation. So then that becomes 1 minus sine squared x minus sine squared x. So then combining like terms, this is going to give us 1 minus 2 times sine squared x. So these are the two other expressions for cos 2x. So now that we have proven all the identities, let's take a look at how we can use them in some harder problems. So to solve this equation here, we know that we need to replace our cos 2x with one of the double angle identity expressions. But cos 2x is the one with 3 possibilities for us to choose from. Now you can either test all of them out one by one and see which one works, or we can take a look at the rest of this equation and see what kind of terms we have here. So we have a 3 cos squared x minus 1. Now 2 of the identities involve a sine squared x, but there is one in there that only has cos squared x. And since we have just cos squared x on the right-hand side, that tells us that we want to maybe choose that one. So let's take a look to see if that works. So we're going to replace cos 2x with 2 cos squared x minus 1. And that is equal to our right-hand side, which is 3 cos squared x minus 1. Now combining like terms is going to give us cos squared x is equal to 0, which means cos x is equal to 0. Now notice how for this problem, we weren't given a domain. So this means we need to find the general solution to this equation here. So to do that, what we need to do is find the solution within one full rotation. So usually between 0 and 2 pi. And then we're going to add 2n pi to it so that we get the general solution. So cos x is equal to 0 when x is equal to pi over 2 or 3 pi over 2. So those would be the two solutions within one full rotation. So that means our general solution would be x is equal to pi over 2 plus 2 pi n, or 3 pi over 2 plus 2 pi n. And n here would be an integer. Now some of you may notice that pi over 2 and 3 pi over 2 are pi units apart. So another way that you can actually write this solution is x is equal to pi over 2 plus n pi, where n is an integer. And both of these would be perfectly fine solutions. Now for our last problem, we want to prove this identity here. So like usual, we're going to start with the more complicated looking side. So that would be the left-hand side. So we start with sine 2x over 1 plus cos 2x. Now sine 2x, we only have one expression for that. So that is equal to 2 sine x cos x. And then in the denominator, we would have 1 plus, and cos 2x is the one that we have three different choices. But the fact that on the right-hand side, we just have tangent x tells us that we should pick something that can help us get rid of this 1 in the denominator right now. And the only one that can help us do that is the expression with a minus 1 in there. So that means we're going to pick 2 cos squared x minus 1. So now our 1 gets canceled out, and we're left with 2 sine x cos x over 2 cos squared x. And now we can see that our 2 is going to cancel, and then our cos x on top is going to cancel out with one of them on the bottom. So we're left with sine x over cos x. And our quotient rule tells us that this is equal to 10x. And that's exactly what we wanted to show, so this is where we can stop. And now let's do a quick recap of what we went over in this video. We have now proved all of our double angle identities, and we looked at how to use them to solve quadratic trig equations. We also learned how to prove other identities with these double angle expressions. And now it is your turn to give this a try. Can you prove this trig identity on the screen here? Make sure to leave your answer in the comments below and let us know if you'd like to see more content on trig identities in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.